In the previous video, we discussed the PIN junction that is used in thin film silicon solar cells. In this video, we will explore the silicon phases and alloys used in these cells. The learning objectives for this video are to understand the difference between the various silicon phases. We will discuss a variety of silicon alloys and how these alloys allow for the deposition of high-performance solar cells. Amorphous silicon is not the only silicon phase used in thin film solar cells. The nanocrystalline silicon phase is a hydrogenated silicon alloy with a very complex structure. Nanocrystalline silicon, which is also known as microcrystalline silicon, consists of small grains that have a crystalline lattice and are a few tenths of nanometers big. The grains are embedded in a hydrogenated amorphous silicon tissue. As explained in the preceding section, silicon films are grown on top of the substrate using chemical vapor deposition. We now start growing a film on such a substrate. The yellow areas represent the crystalline grains, while the brown areas represent the amorphous tissue. The white fractions in the material are cracks and voids. The crystalline volume fraction of the grown film depends on the condition used for the chemical vapor deposition. We can see on the left-hand side a fully crystalline phase. The material is close to polycrystalline silicon, except that it contains more cracks and pores. These cracks and pores are even more pronounced in the first tenths of nanometers of the growth, which is known as the incubation layer. The incubation layer is followed by stationary columnar growth, which is usually up to several hundreds of nanometers. We can see that the crystalline volume fraction decreases from the left to the right, and that the material on the right-hand side is fully amorphous. A measure of the crystalline volume fraction is called the crystallinity, which is defined as the volume fraction of the crystalline phase with respect to the total silicon volume. Depending on the deposition conditions, the crystallinity of the nanocrystalline material can range anywhere from fully amorphous to a mixed phase with a few small crystalline grains to a phase which is dominated by large crystalline grains and only a small fraction of amorphous tissue. An example of a nanocrystalline silicon layer with predominantly crystalline grains is shown in this image of a nanocrystalline silicon single junction cell, which is made using transmission electron microscopy. Research has shown that the best nanocrystalline building materials used in solar cells have a network close to the transition region between the nanocrystalline and amorphous silicon, with a crystallinity of about 60%. Let's now look at the various silicon alloys used in thin film solar cells. We have already seen how silicon and hydrogen are used to fabricate hydrogenated amorphous and nanocrystalline silicon. In a similar fashion, other group 4 elements are used in thin film cells. As you may recall, group 4 elements like silicon have 4 valence electrons available to form bonds. Hydrogenated amorphous and nanocrystalline germanium can be produced, for instance, by alloying germanium with hydrogen. Germanium is often alloyed with silicon to create a hydrogenated silicon-germanium alloy. Similarly, silicon is alloyed with carbon to create hydrogenated silicon carbide. Another interesting alloy is obtained when oxygen, a group 6 material with 6 valence electrons, is incorporated into the lattice. The resulting hydrogenated nanocrystalline silicon oxide is often used in thin films due to its favorable optical qualities. But why exactly do we alloy silicon with these other elements? The answer is band gap engineering. By alloying silicon with different elements, we can produce thin film silicon absorber layers with a range of band gap energies. Let's look at this range. Here we see the AM1.5 spectral power density as observed on the Earth's surface. Amorphous silicon has a band gap energy ranging from 1.6 to 1.8 electron volts, depending on the hydrogen content. So that corresponds to this part of the spectrum, where all energies above the band gap are absorbed and all energies below the band gap are not absorbed. Nanocrystalline silicon has a band gap energy ranging from that of silicon, 1.1 electron volt, to about 1.3 electron volt, as it becomes more amorphous and hydrogenated. This means it already starts absorbing in the infrared part of the spectrum. Amorphous silicon germanium has a bandgap energy ranging from 1.4 to 1.6 electron volts, while amorphous silicon carbide has a bandgap energy greater than 1.9 electron volt. Nanocrystalline silicon oxide finally has the highest bandgap energy of these alloys of over 2 electron volts. This is to be expected since glass, which is silicon dioxide, has a bandgap energy of about 9 electron volts. The high bandgap energies of silicon oxide and silicon carbide allow it to absorb the highly energetic blue and ultraviolet part of the spectrum with minimal thermalization losses. With this range of silicon alloys, we can design several multi-junction thin-film silicon solar cells. Probably the most studied concept is the micromorph solar cell, illustrated in this figure. A micromorph cell consists of an amorphous and nanocrystalline silicon junctions. Amorphous silicon is placed on top since it has the highest bandgap energy. These thin yellow layers in between are the intermediate reflector layers, which will be discussed later in this section. Let's take a quick look at the band diagram of the tandem device. We first have the band diagram of the amorphous silicon top cell, followed by the nanocrystalline silicon bottom cell. The blue and green short wavelength light is absorbed in the top cell, while the red and infrared light is absorbed by the bottom cell. Holes generated in the top cell and electrons generated in the bottom cell can be collected on either side of the device. However, as explained in the preceding section, a tunnel recombination junction is required between the N layer of the top cell and the P layer of the bottom cell, which allows the electrons from the top and the holes from the bottom cell to recombine. The current micromorph cell has an efficiency of 12.7% as manufactured on lab scale by EPFL in Switzerland. Naturally, cells with more than 2 junctions can also be made to even further increase the spectral utilization of the solar cell. An example of a triple junction solar cell is shown here, with an amorphous silicon junction on top, an amorphous silicon germanium junctions in the middle, and a nanocrystalline silicon junction on the bottom. This triple junction device was made by the former US company United Solar Ovonic. The initial efficiency of this current record triple junction cell is 16.3% on lab scale. The reason for adding the term initial will be explained in the next video. The spectral utilization of this device is shown in this figure. We can gather that the spectral utilization is relatively high, especially in the ultraviolet and the visible part of the spectrum. Furthermore, we see that the EQEs of the individual junctions overlap. At 450 nanometers, light is only absorbed by the top cell. Light around 550 nanometers is utilized by the top and middle cell, while light around 650 nanometers is utilized by all 3 junctions. The overlapping EQEs of the junctions are unlike those of, for instance, the 3-5 multi-junction cells, where the EQEs of the individual cells can be considered like block functions. 3-5 based technologies will be discussed later in this course. Consequently, optimizing thin film silicon multi-junction solar cell is a complex interplay between various absorber thicknesses and light management concepts. In summary, we discussed the phase transition between nanocrystalline and amorphous silicon and defined the concept of crystallinity as the volume fraction of the crystalline phase with respect to the total silicon volume. When then looked into the bandgap engineering opportunity provided by alloying silicon with various elements. Finally, we discussed the micromorph solar cell and an example of a triple junction solar cell using silicon alloys. In the next video, we will discuss the challenges associated with the production of thin film silicon solar cells.